All right. Hello there for people who can't join us live just now. Um, so, as we've been saying in the Desire to Learn section the last couple of days, we're going to be mostly teaching in person in class, and that's always the best way to do it. The only definite online lecture cast in stone will be that Monday morning for section one. Everything else will be in person. And if you're in the hybrid class watching this, don't worry. I will continue to make these lectures for about half an hour or 40 minutes every day, Monday to Friday. I might have to change the time a bit, because certainly for some days, like Monday, Wednesday, or Wednesday and Friday, because of course I'm going to be on campus physically teaching. But there will still be a separate set of lectures Monday through Friday for people who want to be just online. That's predominantly the hybrid class on a Wednesday night who only have that opportunity anyway. Okay, so announcements will be made if this time slot moves, and it will move. Maybe to 10 o'clock in the morning. I'll do it live maybe. Okay, so we left off yesterday amid great excitement, I might add, just about ready to look at the three states of matter, which we're no doubt already familiar with, solids, liquids, and gases. But the particular state of matter that you get for a particular compound depends on two forces which are working against each other. And that is the kinetic energy of the molecules. That's really just a fancy way to say the movement of the molecules. And that movement or kinetic energy is very closely tied to the temperature. If temperature increases, molecules move faster and start whizzing around in the room. But as temperature decreases, molecules start moving more slowly. And so the amount of kinetic energy depends on the temperature in the surrounding environment. And of course, that kinetic energy is trying to make matter fly apart, trying to create the most chaotic state of matter, which is the gas state. The gas state is where the molecules have the most kinetic energy, and it's the most random state of matter. Everybody's flying about, whizzing around at 3,000 miles per hour or faster, moving in random directions. Now, working against this chaos that the world is trying to create, we have the forces of attraction between one molecule and a neighboring molecule. So we're talking about an attractive force between an oxygen molecule and another oxygen molecule. The attractive force between a molecule of sodium fluoride and another molecule of sodium fluoride, or another unit. There are attractive forces between molecules and atoms, which are trying to hold matter together. It's trying to create order. And so it has the opposite goal of kinetic energy. Kinetic energy is trying to fly matter apart and create chaos. Bonding forces between molecules are trying to create order. And we see that order holding true when we've got the solid state. In the solid state, all the molecules are tightly squished together and they're packed neatly on top of each other normally, with very little space between the atoms and molecules. And so the kind of state we see, solid, liquid, or gas, depends on which has the greater sway. Is it more about the kinetic energy of the molecules, or is it more about the bonding energy between molecules? Excuse me, I think you can probably hear small children randomly running up and down the corridor in my house at the moment. If it gets really bad, I'll stop and talk to them. Okay, so at low temperature, excuse me, at low temperature, molecules have less kinetic energy. And so the forces of attraction take hold and we create the most ordered state of matter, the solid state. It's like if you're trying to hold on to your kids, if they're moving slowly, they're much more easy to corral and keep a hold of. And so we see this highly ordered state at low temperature for all matter. Solids have a definite volume. They also have definite shape. Like a cube, wherever you place the cube, is going to have the exact same shape and the exact same volume because the molecules are not really moving. Now there is some movement, but it's on a micro scale level. So all the atoms are lined up next to each other, all the molecules. And if I was a molecule, although I wouldn't be moving about, I might be kind of just slightly twisting or maybe just bobbing up and down a bit. Okay, I'm looking weird. But there would be still some very small motion within the molecules, but that's not something we can detect. So definite shape, definite volume, as far as our eyes can tell. The forces of attraction are strong between the molecules, which creates that order, and it's the most highly ordered state of matter. Excuse me one sec, my son has a question. Yes.
No.
Right, sorry about that. He had a Minecraft related question. I don't even play Minecraft. It's mummy that does all that stuff. So that's the most ordered state of matter. Now, as temperature rises, the molecules increase in kinetic energy. They increase in movement. And think of it like two magnets which are locked together. The more I push and pull on one of the magnets, the more likely they are to start moving apart or moving around each other. And this is exactly what happens at the melting temperature for solids. We've reached a temperature, as temperature rises, where now the molecules have enough kinetic energy to start moving around each other. They're still in close proximity, they're still tightly packed because there still is some retained force of attraction, but with their movement, they're resisting that force of attraction and kind of sliding around over and around each other. And so that's why when we melt a solid into a liquid, we still have definite volume. 50 milliliters of water is going to be 50 milliliters of water, regardless of what kind of container you pour it into, but we no longer have definite shape. You pour that 50 milliliters of water into a rectangular vessel, the water takes up the shape of a rectangle. You pour the water into a spherical container, then the water takes up the shape of a sphere. So we do have changing shape because the molecules can move around, but they're still tightly packed. I'm sure everybody's seen that. If you take a syringe full of water, put your finger over the end of the syringe tightly and try and push down on the water. It doesn't budge. You cannot change the actual volume. That's still a definite set value for a set amount of chemical. So we've got the forces of attraction that are still there, but they are weaker. They're not able to hold on to each other as tightly as they were. Like if my kids start moving around, it starts to become more difficult to keep them under control. It's because the molecules are now sliding around each other. There's less order if people start moving around or if molecules start moving around. And then eventually, if temperature continues to rise, we reach that critical boiling temperature for the chemical, where now the molecules have enough kinetic energy to transform into the gas state. So at this point, the molecules now separate from each other, and we're talking about huge volumes of distance between one molecule and its neighbor. If you imagine that my body was a single molecule, as the molecules move apart, the next molecule, from my perspective, would probably be 2 or 3 football fields away. So compared to the size of a molecule, the amount of space from one molecule to another seems absolutely vast. Huge amounts of space, and the molecules are moving very rapidly because of that kinetic energy. So now we do have changing volume, depending on just how high the temperature is. Natural law of things is, the higher the temperature, the faster molecules move, and the more space they take up. Think of it like a group of runners in an athletics meeting. If there's a greater range of speed between amongst the runners, like in a relatively long distance race, they start to spread out more. But if it's just a race for walking, like a 100-meter walk or something, because they're not moving as fast, the total gap between the fastest and the slowest would be smaller. And so that changes the volume that the gas occupies. So increasing temperature means increasing kinetic energy and increasing space for that gas. It's like the molecules are more excited and start moving about more and spread out more. So I've got the solid state, which is the most highly ordered state of matter, but we have very little kinetic energy. We've got the liquid state with increased kinetic energy, increased chaos between the molecules, and then finally the gas state, which is the most chaotic state of matter. And that's because we've got an increase in our highest level of kinetic energy. And pretty much in the gas state, there's no longer any intermolecular bonding forces, no attraction between the molecules. There's just too much space. It's kind of like with two magnets. If you hold them far enough apart, they no longer attract to each other. And it's the same basic philosophy with these molecules. If they're held sufficiently apart, like they are in the gas state, they no longer feel an attraction to each other. Okay. Next piece. Just emphasizing the kinds of reaction we get in chemistry, which mainly falls into two basic classes. We sometimes talk about physical reactions and sometimes talk about chemical reactions. So a physical reaction is just one of those changes in state that we've been talking about for the last 20 minutes. A solid having heat energy applied to it, maybe from a Bunsen burner or a hot plate, heat energy applied, and that solid eventually melts into a liquid at the melting temperature. Or maybe you've got a beaker of water, and that liquid boils at the boiling temperature into water vapor, into a gas. That's all we mean by a physical reaction, just pure changes in state. So the chemical composition of that matter isn't changing. Whether it's ice, liquid water, or water vapor, it's still basically H2O. There's no change to the chemical formula. So we see the chemical formula at the beginning on the left. We see how many units of matter that we're talking about, 8 in this case. 1, 2, 3, 4, 5, 6, 7, 8. We see this arrow, which is implying that there's a change taking place, in this case, a change in state. And that change in state is identified at the end of the chemical formula sometimes. So in parentheses, right at the end, we see S for solid, and then an L for liquid by the end of this particular reaction, and we use G for gas. The only other symbol that we sometimes use, let me just put this up here and over here. This is great using Zoom. I can even put some pencil work in. Let's see. So let me see. Got too many things open on my screen just now. Annotate. So the only other thing we use, look at that, I even got a pen. You'll sometimes see a chemical formula. Let's say it's sodium. Oh, that's not the pen I want to use. Yeah, that's better. Something like, say, sodium chloride. And its state might be given as AQ. Apologies for my terrible handwriting. AQ, which stands for aqueous. And that just means that that chemical, sodium chloride, has been mixed into water to make a solution. So that is the other state of matter which is sometimes given. The chemical is in solution and the solvent used is normally water. So these physical reactions are all about just a change in state, but there's no change in the chemical formula. Other physical properties that we can talk about are things like how soluble a chemical is in water. We could talk about the color of the compound. We could talk about the smell or odor that that compound has, or maybe even the texture or feel of that compound. These are all descriptions of physical properties for that matter. Excuse me. One sec, I'm sorry, one sec. In fact, I think we'll just make it a standard thing for the morning lectures to take a quick 5-minute break in case people would need the bathroom or something like that. And we did that yesterday anyway, so let's take a 5-minute break and we'll come back at 11:30, okay? My daughter has a desperate need for a lollipop. And we're back. Okay, so probably another 15 minutes or so, 10 minutes. So when we're dealing with a chemical reaction, on the other hand, there is a change in chemical formula. That might involve a change in state as well, but more importantly, there's chemical change. And it's really just like cooking. Excuse me, cooking. You take your raw ingredients, and then over the course of the cooking, you transform those raw ingredients into that wonderful product, which might not look like anything that you had started with previously. Change the chemical formulas, you change how the chemicals look, feel, sound, and how they react. So a fairly straightforward example, something like HCl, hydrochloric acid. Note that it's given the state of AQ, which means that that HCl has been actually dissolved in water to make a solution. That's mixed with sodium hydroxide. The OH has a special name that we'll talk about in a later chapter. Sodium hydroxide, which is also AQ, aqueous. That's also been mixed into water. And then we've got this reaction arrow to represent the chemical change which is taking place. So the chemicals on the left are the chemicals which are being used up. And the chemicals on the right are the chemicals which are being produced as a result of this chemical reaction. So the HCl and NaOH disappear. We replace it with H2O, water, which is a liquid at room temperature, and then sodium chloride, which is a solid at room temperature, basically just table salt. So although there's been chemical change, we account for all of the chemicals in this reaction. We started with one hydrogen there and another hydrogen there, and by the end of the reaction, we still have two hydrogens. They just happen to be part of the same molecular product. We started with one chlorine atom. We're finishing with one chlorine atom amongst the products. We started with one sodium, and we started with one oxygen, and we're finishing with one oxygen and one sodium. So there is an accountability. All those Lego bricks, those particular kinds of Lego bricks and elements, all the elements which went into the reaction come back out in the same proportions. So we don't mysteriously lose anything or suddenly produce something that we can't account for from amongst the initial reacting materials. So the chemicals we start with are called the reactants. The chemicals we finish with are what we call the products of the chemical reaction. Likewise, nitrogen reacting with oxygen gas. Chemical change occurs. That's what the arrow is trying to tell us. There's a change. We know there's chemical change because there's a change in the formula. Now we've got these nitrogen oxygen units, or nitric oxide as it's known. And again, in a later chapter, we'll talk about how to name chemical compounds. That's not something I would expect you to be able to do now. All you need to do from an equation is recognize that we had one formula at the beginning and different formulas at the end. So that's a chemical change, not a physical change. And every element and the number of atoms for that element transfers to the other side of the reaction. These are the chemicals we're starting with. These are the chemicals we're using up. And these are the chemicals we're producing. So while that chemical reaction is ongoing, there are quite often ways that we can tell that chemical change is occurring. If you're holding the test tube or the beaker where the reaction is being conducted, it could be that that beaker suddenly feels very hot or warm to the touch. That's because the chemicals, which have a certain amount of energy, are giving some of their energy away. And that energy is given away to the surroundings, and so it heats up the surroundings. So reactions which give out energy feel hot. Conversely, It could be that the chemical reaction starts to feel very cold to the touch. And that's because we've got a reaction which needs energy to make it happen. And so it takes that energy from its surroundings. And therefore the surroundings, when they lose energy, get colder. Like we were talking about with the three states of matter, the energy of the molecules is very closely related to the temperature. As temperature rises, they have more kinetic energy. As temperature drops, they have less energy. And so a reaction which is consuming energy means that there's less energy in the surrounding environment. And so that feels colder. We often see these kind of things with ice packs for injuries, sports injuries. You basically snap the pack, and that allows two chemicals to mix together. And when they mix together, they react, and it causes an absorption of energy to the chemicals. And so the surroundings feel slower. Sometimes it could be about a reaction which causes a change in state. Take two chemicals which are soluble in water, but when they mix together and chemically react, they produce a new chemical which is insoluble in water. When that happens, we call that the production of a precipitate. Just a fancy word to say that a solid has been produced. We can tell when a solid has been produced because you can no longer see through the beaker if there's enough of it. So we sometimes can tell that chemical change has occurred because we've produced this new chemical which previously wasn't there because we didn't see it. It could also be that the reaction starts with a chemical which is insoluble or starts off as a precipitate, and then over the course of the reaction it gets used up and converted into a chemical which is soluble in water. So sometimes chemicals can disappear during the course of a reaction. Be careful though, because most chemicals are more soluble as temperature rises. So if you're just heating up the solution, it could be that it's just actually becoming more soluble. But if there wasn't a change in temperature and a chemical continued to disappear, it could be a sign that that chemical is being used up. So the appearance of a precipitate or disappearance could also be a sign of chemical change. If your solution starts to bubble and froth, what we sometimes refer to as effervescence, that's just as a kind of old snooty, snobby thing for chemists to say effervescence. Just really trying to avoid saying bubbling. See, bubbling, it's because one of the products produced is a gas. And so it quite literally just bubbles out of solution, like a fizzy drink going flat as the carbon dioxide leaves the drink. Sometimes it could be something as subtle as just a slight color change in solution. Different chemicals absorb different wavelengths of light and therefore produce different colors to our eye. And if we produce new chemicals, which could absorb a new wavelength of light, we could get a different color produced. So color changes could also be a sign of a chemical reaction. Just quickly, I want to go over some practice questions. These are some of the kinds of questions you might see in a homework or a chapter 1 assignment. So I'll just go over these ones quickly with you, and then we'll call it a day then, and then we'll come back to this tomorrow and get on to the metric system. So here's a chemical reaction. It's a nitric oxide reacting with oxygen. That's sometimes referred to as a combustion reaction if something is reacting with oxygen. And it's producing this new chemical, nitrogen dioxide. And so the questions listed are nitric oxide NO can best be described as, so we look at where the chemical is listed on the chemical reaction. Is it on the left side or is it on the right hand side? And so for the nitric oxide, it's listed on the left. So it's one of our starting materials, our initial ingredients. So we describe it as being, in my horrible handwriting, a reactant. Nitrogen dioxide, NO2, because it's written on the right-hand side, this is where the reaction finishes. The traffic's heading in this direction. This is the chemical we're trying to produce. So it's our primary product of the reaction. How much nitrogen dioxide is there when the reaction is finished? So the nitrogen dioxide, of course, is a product, and of course, that actual amount has been left blank. But just as there's an economy of the elements being used, there's an economy of mass. Whatever the total mass going into the reaction is, that has to be the total mass coming out of the reaction. Now, it can be tricky when there's multiple products produced, because all you would say for sure is that they together would total to the same amount being used. But because we've just got one single product, 60 grams plus 32 to give 92, we can say that we should be expecting 92 grams of nitrogen dioxide to be produced, because that's only if the reaction works with 100% efficiency. Reality is that some reactions leave some leftover materials which are unreacted, but even if that does happen, the total mass at the end of the reaction should be exactly the same as we started with, in this case 92 grams. So if all goes well, we expect to produce 92 grams. This is what we sometimes call the conservation of mass. It's one of our chemistry laws. Total mass going into a reaction will equal the total mass coming out of a reaction. How much nitric oxide, NO, is there when the reaction is finished? The nitric oxide is one of the starting ingredients, and we're hoping it's going to be used up. So keeping our fingers crossed and assuming that everything works perfectly, there shouldn't be any of the nitric oxide left over by the end. If 120 grams of nitric oxide is used, how much nitrogen dioxide would be produced when finished? So normally we use 60 grams. We're suggesting that the reaction use 120. 120 compared to 60, that's twice as much. And we'll get into this in much more detail later on in chapter 5, where a reaction is like cooking. If you double the proportions of your starting ingredients, like so if we doubled the amount of oxygen being used, you would expect to double the proportions of the product as well. So if that was the case, I don't know why my little line is missing there. If we're using double the starting reagents, we expect double the final product, and that would be 184 grams. Again, that's only if it was a 100% successful reaction. Often it isn't. If the reaction used 30 grams of the nitric oxide instead with a plentiful supply of oxygen, that's not double anymore, that's just half the amount. So just like any good cooking recipe, if you use half the amount of starting ingredients, you expect to make half the amount of product or half the number of cupcakes. So instead of producing 92 grams, we would produce just 46 grams of the product. Double everything, you get double the products, hopefully. Half everything, you get half of the products. And then what observations could you make to convince you that the reaction was working? Well, let's see, starting materials and products are all gases, so there's going to be no sign of a precipitate. Depending on whether the reaction gave off energy or consumed energy, the reaction flask might be hot or cold, but as we are looking at it here, the big sign would be that we'd now produce a gas that had this orange to red color. Our two starting materials don't have any color associated with them. So any orange-red gas which appears must be due to the product being produced. And as the intensity of that color increases, it's an intensity or an increase in the amount of product being produced. Any questions about those ones? I think that's the only ones on this page. Yep, that was it. Try and line it up. Okay, there we go, got it. So we'll go again tomorrow for another 40 minutes or so. Let's see, that should take us into the metric system. That's a good one to catch tomorrow. That's the big part of the chapter, looking at the metric system. And that's what our first face-to-face laboratory will be based on next week. The metric system and metric conversions, as well as a couple of reactions, and looking for your observations about signs that a chemical reaction has occurred. Let's see, the only other thing to mention. So when we get to campus next week for all the sections and we're doing lecture, we're going to kick off from where this lecture finishes tomorrow online, okay? Everybody's having to use online lecture today and tomorrow. And so wherever I stop tomorrow at 11:45, expect your campus face-to-face lectures to start at that point. Unless, of course, you are section 1 and you have that obligatory lecture on Monday morning as well. Okay. Right. Thanks for keeping me company, guys. I hope that helped a little bit. And we start to get into the juicy stuff tomorrow with the metric system. Have a good day and stay safe.